When we look at the motion of an object from point A to point B, there's an infinite number of paths that can be taken. There's a direct path, but we see here two different alternatives to that. And in fact, there are many different possible paths that could be taken from point A to point B. When we're looking at energy, when we're looking at work done, which gives us energy, part of that is the force that is applied and the distance over which that force is applied. And when we look at those types of forces that act on our objects as they move, we are going to distinguish those forces into conservative forces and non-conservative forces. When we consider a conservative force, for example, is gravity. Gravity always points in the same direction. And that's a typical hallmark for a conservative force, that once the system is set up in a certain way, the force is in the same direction, as long as the system is in a certain arrangement. So what we're seeing here is that if we go from point A to point B along path 1, for part of the time we're going mostly vertically, and we are doing a lot of our interaction with gravity. Later on, we're moving mostly horizontally, and so there's much less interaction due to gravity, and we end up at point B. And from what we've seen, the work done by gravity and the potential energy due to gravity depends on the change in vertical height, because we said that the work done by gravity is the dot product of the force of gravity and the displacement as we move along the curve. So only the vertical component of the displacement will affect our energy due to gravity. We see the same thing when we follow path 2. If we follow path 2, some of the time we're going horizontally and we don't feel very much gravity. Some of the time we're going vertically and we feel much more gravity. But if we look at the total, our total motion, we still have the same net vertical displacement. We'll have the same change in potential energy. And that's what we mean by a conservative force. For a conservative force, you have a change in potential energy, which corresponds to a total amount of work done as you go from an initial point to a final point. As you go from point A to point B, gravity does the same net work following path 1 as following path 2. You do more work, gravity does more work at the beginning and less work at the end for path 1. Gravity does less work at the beginning and more at the end for path 2, but the total amount of work is the same as we go from this initial to final points. And thus it's a conservative force. Thus, whatever work it does to begin with, you can get that energy back again, and hence you can make you can have a potential energy associated with that. The alternative to that, the alternative to a conservative force, which typically points in one direction, and thus, for example, with gravity, if you are going up against gravity, you are doing work against gravity. If you go up and down against gravity, sometimes you're doing work on gravity, sometimes gravity is doing work on you, but when you add it all together, sometimes you have negative work of gravity, sometimes positive work of gravity, sometimes negative work of gravity. It all averages out as if you were just going up against gravity, because gravity is conservative. If you have a non-conservative force, typically that means the direction of the force is changing depending on which path you take, depending on how you travel. In that situation, it would matter which path you take, because the force is going to be different depending on the path you take, and thus the total amount of work is going to be dependent depending on which path you take. And because of that, the work done depends on path. It doesn't just depend on the initial position and the final position, and thus we can't have a potential energy associated with a non-conservative force. Consider a situation where you have an object that slides up and down a slope with friction. It slides up the slope and then it returns back to the same position, but when it comes back down, it will have less kinetic energy. The reason for that is that as it slides up, a part of its kinetic energy is transformed into gravitational potential energy, but part of that kinetic energy is transformed into thermal energy. When you convert your mechanical energy to thermal energy doesn't have the potential to be transformed back into kinetic energy. Thermal energy is still there, but it's useless to us from a mechanical point of view. It can't be used to do anything. What happens furthermore is when the block slides back down, even more kinetic energy is lost to thermal energy. And this is what we're talking about, the direction of the force changing. As the block goes up, the force of friction is down. Once the block gets to the top and turns around, the block will go back down, and now the force of friction is upwards, is against that motion. And so what you're seeing there is that force of friction is always resisting you, it's always taking energy away, it's never going to give that energy back, and thus it cannot be considered a potential energy, because the potential energy is the potential to give that energy back. The same way that you do work on gravity as you lift an object, gravity does work on you as you lower the object. You do work on gravity as you lift an object, gravity does work on you as you lower the object, and thus gravity will give you that energy back. With a thermal energy, with a force of friction, that is a non-conservative force, because you're never going to get that force back, or that energy back. So friction and drag are non-conservative forces, because there's no frictional potential energy. Once that energy has been removed, it's inside the system, but it's lost. It's not mechanical anymore. Also, tension and thrust are non-conservative. They're changing direction as you go around, and so you can't use that energy to get, you cannot use those forces to get energy back. With all of this information in mind, we revisit the energy principle that we talked about before. We imagine a system here that is composed of three different particles that are interacting with each other, and also have external forces acting on them, which give them external work coming in from the environment. With the new information that we have, we know that the forces of interaction between these objects can be conservative, and they can do conservative work, meaning that they can change potential energies of each other, or it can be non-conservative, which means that as they do work, that energy is lost to thermal energy. When we're talking about non-conservative forces here as well, we're going to distinguish between dissipative forces, which would be like friction, and external forces, which are outside of the system, acting on the system, and adding or taking energy out of the system. Our dissipative forces are like friction or drag. They're going to transfer energy into thermal energy, which is still present in the system, but is not mechanical energy, is not useful for anything. The external forces can add energy to the overall system or take that energy out. Thus, when we look at the overall system, we've said that the total energy of the system is the kinetic energy of the system, the motion, plus the potential energy of the system that's stored in the interactions within the system, and the thermal energy of the system. We define the potential energy and the kinetic energy, that is the mechanical energy of the system. And so that's the motion aspect. The thermal energy is the heat of the system, which for right now is present but is not helping us. We can't do work with that. It doesn't affect our motion. And this is the energy of the system. We've typically said that the energy of the system, the change of the energy of the system is zero, and that's how we've said that the total energy is conserved. And we've talked a lot in this module about conserving energy when the total energy of the system is zero. However, that's not always the case. Sometimes, instead, there's external work that's being done by external forces that are adding energy to the system, or external forces that are taking energy out of the system. In that case, the total energy of the system is no longer conserved. This whole equation is quite complicated. There's a lot of things going on. But, number one, these are all scalars. These are all amounts, and so they make it a lot easier to deal with here than they were in Newton's laws when everything was a vector and we had to deal with the direction of everything even as it changed in time. Furthermore, a lot of the time we don't have all of these different terms. A lot of times, for example, we can throw out thermal energy if there's no friction. We can throw out spring potential energy if there are no springs present, etc. we can simplify a lot of the terms. What happens many times as well is that if we do have an isolated system, that means there's no work done by external forces. And if there's no external work done, then the change of energy is zero, and thus for an isolated system, the total energy is conserved. So a lot of times we can simplify this equation, and even still, even when we do have to deal with every part, we have an expression for kinetic energy. We have expressions for potential energy. We have expressions for thermal energy, etc. And so even when we do have to consider everything here, it's still a lot of individual terms. Even though there's a lot of terms to keep track of, each individual term is fairly simple and is a lot easier to deal with than it was under Newton's laws. But to recap, we have a whole system. That whole system includes an object or objects that have kinetic energy and potential energy. There's an exchange of mechanical energy between these two. And if there's friction in the system, as you have this exchange of energy between kinetic and potential energy, you have friction that's taking away thermal energy. So the system is heating up, but it's at the cost of loss of kinetic or potential energy. All of these energies are the total energy of the system. That total energy of the system is conserved if the system is isolated. If there's nothing coming in or out, there's no change in internal energy, and all of the energy is conserved. If there are external forces, the change of energy in the system is the work done by those external forces. We can look at the forces we have bringing energy in, transferring energy into the system, or forces, external forces that transfer energy out of the system.